This is the third problem in the QHack 2023 Quantum Coding Challenges, and it's entitled A Sure Thing. And what we're being asked to do here is to basically implement Shor's 9-qubit code, which it's responsible for guaranteeing that if we have a state psi and there's a chance of undergoing some bit flip errors or some phase flip errors, that we can correct for them. Now that requires a total of 9 qubits to do that. And the circuit is actually just given to us. So in this problem, all we need to do is just code these gates. I am not going to go over the specifics of how the circuit works. If you're interested in that, let me know and I can share a link to a good resource on this. But I think it's still worth going over how just to put the gates into the circuit and look at some ways in which we can do this with less lines of code, and also how do we get what we're being asked to do at the end of the circuit, which is compute the expectation value of the poly Z operator on each qubit independently. So I think that's a good thing to learn if you're coding in pennylane. So keep watching the video if you're interested. All right, so let's go ahead and first, as always, import pennylane as QML, and from pennylane import the autograd version of NumPy as NP. And let's first look at the function that is already given to us that implements this error here in the middle, which I think it's interesting to understand how it works. So this is, again, given to us already, and the way this is done is by creating a dictionary where we have a poly X, a poly Y, or a poly Z corresponding to the keys 0, 1, or 2. And the way the error is introduced into the circuit is by using this function called error, which is going to take the error key, which is basically what error we're going to apply, 0, 1, or 2, and a qubit. So that corresponds to which of all these qubits the error is going to be applied to. So it could be a poly X, a poly Y, or a poly Z gate applied to any of these qubits, and this circuit will guarantee that we can generate some syndrome out here at the output that would tell us where that error is, and we can use that to then correct for it. So the way this works is that function takes, again, the error key and the qubit and uses this get attribute function in Python, which just basically we pass here from this dictionary either the string poly X, poly Y, or poly Z, and from this QML object it just extracts the gate we want and applies it to the qubit that we're passing. So that's all that does. Now the next thing we need to do is specify that we're going to have 9 qubits. So the number of qubits equals to 9. And then the device, as always, we're going to use QML device default qubit. And then wires equals to n qubits. Next, we're going to create our Q node, which is going to use that device. And then we're going to define our function that takes as an input the state. So if you see here at the input, we're going to have some arbitrary state psi. So we're going to pass that as a parameter to this function. Then we're going to pass the error key, which is going to be what type of error gate we're going to apply, and then the qubit to which we're going to apply the error. Now, I'm not going to code step by step this for you. It is just going to be boring to watch me just type in all the different gates. So what I'm going to do is I have the circuit already here, so I'm just going to copy and paste in there. So let's do that here. And as you can see, I have a CNOT gate between qubits 0 and 3 and 0 and 6. So those two are this first two CNOT gates. Then I think this is interesting to highlight. I'm using this QML broadcast function, which allows me to avoid having to repeat the application of these 3 separate Hadamard gates. So what I just say is use broadcast on the Hadamard gate and apply to wires 0, 3, and 6, and use this pattern single. And single just means that I'm using single qubit gates. So as you can see, that's in qubit 0, 3, and 6. And then I'm going to do the same thing for this CNOTs. So I just need to now pass all the qubits that the CNOTs will be applied to. So in this case, it will be 0, 1, 3, 4, 6, 7. And as you can see here, I have 0, 1, 3, 4, 6, 7, and I'm applying CNOT gates, but I'm using this pattern double. That means that the CNOT gate will be applied to 2 qubits instead of just 1, instead of this single, right? Because it's a 2 qubit gate. And same for the next CNOT. Then we're just going to call that function we define up here that is going to apply that error gate to whatever qubit we're specifying. And as you can see, the following circuit is very similar to what we have here before. We just have those same CNOT gates, and then we have some Toffoli gates, and then the Halamars again. And as you can see here, I have, again, using this broadcast, the CNOT gates, the Toffolis, and then broadcast to apply the Halamars, and then a few CNOT and Toffoli gates here at the end, right? Now, since we're being asked to return the expectation value of each qubit on the poly-Z operator, what we need to do here is find a way to guarantee that we're calculating all those different expectation values. So how do we do this? So let's take a look at a simpler example where we have, for example, let's create a device called device 2, QML device, default qubit, and I'm going to use just 2 wires. Then I'm going to create my Q node on device 2 and a function, let's call it QN, just with, let's say, a Halamar gate on qubit 0 and a CNOT gate between qubits 0 and 1. And now, for now, let's just return, let's say, the expectation value on the poly-Z observable on qubit 0, right? We know how to do this. And then let's just print our circuit just to take a look at it. And here I'm missing something. I forgot to write down QML here. Okay, so we have here, as you can see, I'm computing the expectation value of the poly-Z observable on qubit 0, right? But what if I want to do that for qubit 0 and qubit 1? Well, I can't really, do the tensor product of the two of them, right? Because that observable is actually the ZZ observable of this circuit, is not the Z on qubit 0 and separately the Z on qubit 1, or in other words, Z tensored identity and identity tensored Z. So in order to get 2 separate expectation values, 1 for each qubit, what we need to do here is actually just return 2 separate expectation value objects. So here I'm just going to copy and paste and put a little comma here and then do it on qubit 1. And that way we get the expectation value. Now, to clarify, this is the same as doing QML poly-Z tensor with the identity on qubit 1. And this is the same as doing the identity on qubit 0 tensored with the poly-Z on qubit 1. So now for this Shor circuit, where we have a total of 9 qubits, well, we could go ahead and just, do this 9 times, right? Write 9 times this QML expectation value of the poly-Z on each of the qubits. Now, the good thing is that in pennylane, we can do this by returning actually a list. So we can use list comprehension here, where we do QML xval on QML poly-Z on, let's say, qubit I, or let's just call it wire, right? And then I can do here for wire in range and qubits. So, or, if it's clearer, let's do this for qubit in n qubits, for qubit in n qubits. And And pennylane understands that by returning this list, what I'm doing is returning each of the expectation value on each of the qubits. So here, let's go ahead and print or draw the circuit, QML draw. And actually, let me first execute this, because we're going to have to pass some parameters to this function, right? We need to pass the state, the error key, and the qubit. So we can, for example, say that our state is going to be state 1. So we pass this list 0, 1. Then error key, we can say, okay, let's apply poly X, so that will be error key 0, right? Remember, we have this error dictionary, so 0 corresponds to a poly X. And then let's apply it on qubit 3, for example, right? And now I can go ahead and draw our circuit, right? So draw Shor, and I need to pass this 3 parameters. So let's just actually copy them from up here, because I named them the same way. And let's also print the output, right? Let's print the that expectation value on each qubit. So let's just maybe copy and paste this down here. And instead of doing QML draw, we're just gonna call that circuit Shor with these parameters. And here we have it. So first we are preparing that state psi, and the 2 C0s, the Hadamard gates, and so on and so forth. And then at some point here, we're applying that error gate, which I'm not sure. Oh, here it is, I think. This is the error being applied on the 3rd qubit, right? 0, 1, 2, 3, and it's a poly X. And this is the output of the expectation values on each of the 9 qubits. Now, here I selected these values because this is what's given to us as an input to check our problem. And here we can see that the output is expectation values of -1 on this 0th entry, and then -1 here and here. All the rest are 1s, and here we can see that our output matches. Now, just for fun, let's say we're gonna apply this to qubit 5, and then error key, let's say, is gonna be 2. So we apply now a poly Z error on qubit 5, and here if we redraw the circuit, we can see it here, down here, being applied, and then obviously we get a different list for the expectation values. So I hope this was helpful, and if you have any questions, let me know. Hope to see you in the next video.